Hello and welcome to section 13.3. This section deals with what are known as inverse functions. And before we get into inverse functions, I first want to just recall a few things about functions themselves as well as what are known as relations. So we'll go ahead and start with relations. And we say that a relation is a pairing between sets. So if I have a set of numbers, say the numbers 1, 2, 3, and another set of numbers, say 4, 5, and 6, I can create a pairing between these sets as follows. And I'll just make one up just to illustrate. So let's say 1 is paired with 6, 2 is paired with 4, and 3 is paired with 5. Okay, so this pairing you see between these two sets of numbers is what we call a relation between these sets. And some terminology here, we have what are called ordered pairs for a relation. So we think of this first set of numbers as the inputs for the relation and the second set as the outputs for the relation. So if I input the number 1 into the relation, it will output the number 6. If I input 2, it'll output 4. If I input 3, it'll output 5. Okay, and we typically label the inputs with the variable x and the outputs with the variable y. Right, this is really just the same thing you see when you're graphing ordered pairs in the xy plane, right? Now I can go ahead and represent this particular relation with ordered pairs as follows. So we have the input 1 goes to the output 6. The input 2 goes to the output 4. The input 3 goes to the output 5. Okay. One other piece of terminology, the collection of inputs are what are referred to as the domain of the relation. In the collection of outputs, that's referred to as the range of the relation. All right, so here's another example. Let's say I have the relation that sends 1 to 5, 2 to 4, 2 gets sent also to 5, and then 3 gets sent to 6. So I could write down this relation as a collection of ordered pairs as well. 1, 5, 2, 4, 2, 5, and 3, 6. Okay. And one thing to notice here is that the input 2 is actually sent to more than one output, right? Sent to both 4 and to 5. All right, and now this is going to lead us to a discussion of functions. Okay, so what is a function? Well, a function is just a special type of relation. Okay, it's a relation where each input x is mapped to only one output y, or in other words, each x corresponds to only one y. So looking at these two examples, which one is a function and which one is not? Well, number 2 is not a function, and that's because the input 2 corresponds to more than one y, right? It corresponds to more than one output. So this is not a function. Whereas looking at the first example, well, each one of these numbers, the 1, 2, and 3, is sent to only one output. So this is a function. Okay, great. So now when you're working with a function, okay, we can use what's referred to as function notation. That's the next thing we're going to look at here. And the idea with function notation is really in part just to highlight input-output pairs. Okay, so I could think of a function as a type of machine. So I'm going to feed the function, and we'll use the letter F for function, of course, to denote our particular function rule. So you feed this function some input x, it does something to that input, and it spits out this output y. And to highlight that y came from the input x via this function f, we write y equals f of x. Now notice when working with function notation, this is not f times x. Oftentimes in math, parentheses denote a multiplication. That's not what's going on here. Here we read this out loud as f of x, and we're writing this now again just to highlight that the output y comes from this particular input x. So going back to that first example we saw, this was where 1 gets sent to 6, 2 gets sent to 4, 3 gets sent to 5. Okay, I can write all of those input-output pairs using function notation as follows. So if I do f of 1, that's saying feed the function the input 1, the output will be 6. If I feed the function 2, the output will be 4, and if I feed the function 3, the output will be 5. Okay. Now if I'm given an equation for a function, like f of x equals 2x minus 7, and I plug in different values for x. In other words, I feed the function different inputs. Well, I'm just going to plug in, or in other words, replace x with whatever the input is. So if I feed it 0, I get 2 times 0 minus 7. That would just be minus 7. And that's telling us for the input 0 for x, the output y would be minus 7. If I feed the function, say, negative 2, 2 times negative 2 minus 7, that'd be minus 4 minus 7 is minus 11. Again, the input here, x is negative 2, the output is negative 11. All right, cool. So now let's look at another example here. And let's say for this example, I have something like this. 1 gets sent to 4, 2 gets sent to 4, and 3 gets sent to 6. So as a collection of ordered pairs, I would write this as 1, 4, 2, 4, and 3, 6. If I wanted to write these input-output pairs using function notation, I could do that as follows. I'd say that f of 1 is equal to 4, f of 2 is also equal to 4, and then f of 3 is equal to 6. Okay, so these are just the various representations we've seen up to this point for functions here. All right, so now notice in this example, it is a function. Each input goes to only one output. But what makes this one a little bit different than what we've seen up to this point is the fact that the number 4, the output y, is coming from more than one input x. It comes from both 1 and 2. So this leads us to what we refer to as a one-to-one function. So a function is one-to-one, and I just abbreviate that 1, 1, if each output y comes from one and only one input x. And you see here in this third example, this thing is not one-to-one. And the reason being is that the output y equal to 4, this comes from 2 inputs, okay? It comes from x equals 1 and x equals 2. Okay, so this is not one-to-one. This first example, on the other hand, though, right? Each one of these outputs, each one of these y's comes from only one input. So this is a one-to-one function. All right, great. So now with all of that in place, let's go ahead and check out the first, here I'll bring that back up. Let's look at the first problem on the worksheet. So here we're looking at the question that says, determine whether the given function is one-to-one. And here in part A, we're given a formula for the function f of x is x squared. And so the question is it possible for a y output to come from more than one x input? If I plug in a couple of values for x just to get a feel for what this function does, well, the function just says take the input x and square it. So I'd square negative 2 to get 4. square -1 to get 1, square 0 to get 0, square 1 to get 1, square 2 to get 4, so on and so forth. All right, so now notice here, the output 1 comes from more than one input. It comes from both -1 and 1. That alone says this thing is not one-to-one. Okay, you could also point to the output 4, right? That comes from more than one x input. It comes from -2 and from 2. Okay, now if I were to look at a graph of this function, this is just y equals x squared, and we know what that looks like. It looks like this, right? Just our standard parabola-shaped curve. And notice now with these particular input-output pairs, -1, 1 and 1, 1, we're seeing these points on our graph, -1, 1 and 1, 1. And then likewise for -2, 4 and 2, 4. Okay, now the big takeaway from this, okay, is that this thing, well, one, it's not one-to-one. We know that from just looking at the table. But looking at the graph, okay, the failure to be one-to-one can also be seen by the fact that these horizontal lines intersect our graph in more than one place, right? So if I draw a horizontal line, say at y equals 4, I'm asking how many places can that line intersect our curve? Every intersection point is going to correspond to an ordered pair. And since we intersect more than once, we have more than one input going to that same output. Okay, so keep this in mind as we move forward. All right, so now let's look at b. G of x is the square root of x. Well, again, I'll just plug in a few different values for x. Like let's say 0, 1, 2, 3, 4, so on and so forth. So now I'm taking the square root of the input. So this would be the square root of 0, which is 0. The square root of 1 is 1. The square root of 2 is just the square root of 2, which is about 1.41, blah, blah, blah. Square root of 3 is the square root of 3. Square root of 4 is 2, so on and so forth. Okay. Now, if I were to graph this thing, this turns out to be a parabola sort of on its side, so to speak. Okay. But here's the deal. Any one of these numbers, any one of these output y values, can't come from more than one input. And we can see this graphically. Again, if I ask, well, if I draw a horizontal line, how many times can this horizontal line intersect this curve? Well, each one of these horizontal lines is going to intersect only once. Okay, so only one intersection per horizontal line. This thing is one-to-one. So this is one-to-one. Each y is going to come from only one x here. Okay, part C, well, very similar. Just go ahead and plug in a few values of x. So if I plug in, say, -2, -1, 0, 1, 2. Now I'm cubing the input. So I'd get -8, -1, 0, 1, 8, so on and so forth. The graph of this function looks like this. Okay, and again, each one of these output y values is going to come from only one input. Okay, we're not going to have this sort of doubling up effect. Okay, the number 8 as a y output, it can only come from 2, right? So here again, we're saying that this thing is one-to-one. Okay, each one of these horizontal lines will intersect our graph in only one place. All right, now part D, this gives us a collection of ordered pairs, asking is this one-to-one? Well, do you see any inputs any outputs that come from more than one input. 4, right? The output 4 comes from the numbers 3 and from 6. So the answer here is this thing is not one-to-one. Okay, and that's because the y output of 4, this comes from more than one input, x equals 3 and x equals 6. All right, and then lastly, E, okay, is this graph representing a one-to-one function? Well, again, if I look at any horizontal line, is it possible for a given horizontal line to intersect our graph in more than one place? And the answer there is no. Each one of these horizontal lines will intersect in just one place, so this is one-to-one. Okay, that's a good place to stop. Thanks.